I'll see you later.
Okay, hey, thanks a lot.
Okay.
Okay, I'm just talking. Let me put my mic on. I have it on. Just talking with our trusty TA here, Shaunuk. And he informed me that people are asking about when the midterm might be. I'll start looking into that. Typically, we have the midterm right before the break, or somewhat before the break, or somewhat after the break, like the week after the break or the week before the break. Some people like it the week after the break because it gives you a little more time to study for it. Well, let me look ahead and see what we have, and I'll try to scope it out. Okay. 190, and we should be at session. Let's see. Looks like we should be at session 8 here. Okay, and we're continuing on with the portfolio theory, and we're continuing on with the portfolio diagram lemma. Which is not really a lemma in the true sense of the word. Okay, but here's what we get. We get a picture that looks like the following. An R bar P, sigma P. So we have expected rate of return of the portfolio and the risk for the portfolio. And for our problem, if we get something that looks like something like that, and then we get something that looks like here. We get a triangle that looks like this. Here. And what we get is the following. We get this leg corresponds to row 1, 2 equals plus 1. We have two legs that correspond to row 1, 2 equal minus 1. Remember, because then we got the square root of a term, and that term must be positive or at least non-negative. Otherwise, we get a complex root, which we don't want. Okay. And we also did something here. We went something like this. And we said that in the middle here was row 1, 2 equals 0. Okay. And for row 1, 2 equals 0, I should have put this out a little more. For row 1, 2 equals 0, the minimum variance or standard deviation or risk portfolio had sigma p less than sigma 1 and also less than sigma 2. Okay, so at 0, if uncorrelated, we could actually get a portfolio variance if we mixed 1 and 2 further than that. Okay, now, so the portfolio diagram lemma said that all non-negative This would be with W1 greater than or equal to 0, combinations of 1 and 2 lie in this triangle. Okay. Now, suppose we would do the following. Let's look at the short sales case. In the short sales case, we're going to get the following. In the short sales case, we could go up this way, or we could go down this way. Okay, so let's look at what they are. If we go up this way, this corresponds to shorting asset 2. Because now you're going to get a W, and this will correspond to W1 greater than 1. And here, we're going to get shorting asset 1. And here, we're going to get a W1 less than 0. Okay. So right away, you can see that it wouldn't make sense to short asset 1, which asset 1 has the higher expected rate of return. Here, what's happening here is that you're getting, if you short asset 1, you get a lower expected rate of return, but you still get higher and higher risk. Whereas if you short asset 2, you get a higher expected rate of return at the cost of a higher risk, of course. There's no free lunch here. So let's look at this here. And recall our data. Our data is the following. We're going to use the data from that we had before. Would be, let's put it here, I, R bar I, sigma I. Let me write this small. I'm sorry. I'm just going to do it here so I have it. 14, 8, and 6, and 3. Okay, good. And let's let row 1, 2 equal 1/2. And we're going to consider shorting now. Let's do a summary of computations for shorting. Okay. So what are we going to have? Let's do W1 equals -1, minus 0.8, minus 0.6, minus 0.4, minus 0.2. We're not going to do 0 because we know if W1 equals 0, we're at the 2. And then we're going to do plus 0.2, plus 0.4, plus, this should be plus 1.2, plus 1.4, plus 1.6, plus 1.8. Here we're going over 1, and this is plus 2.0. Okay. So let's look at this. if we have negative values of W1, what does that mean? That means we're shorting asset 1. And if we have values greater than 1 for W1, this means that we're shorting asset 2. Okay. So let's put some data down here, and then maybe we'll do a couple of computations here. So we want R bar P equals, okay, so let's read across. R bar P equals 2.0, 3.2, 4.4, 5.6, 6.8. Okay, so it's going up as W1 gets more positive. Then if we look at values of W1 greater than 1, we should get an expected rate of return which is higher than that of asset 1. And in fact, we do get that. We get 15.2, 16.4, 4, 17.6, 6, 18.8, it's going up by 1.2. And in the same way it did in the negative side, 18.8. Of course, the R bar P, the expected rate of return on our portfolio, is linear in W1. And then we get 20 here. So these values are linear in W1. Now, let's look at the portfolio risk as measured by the standard deviation. Here we're going to get the following. Let's just put some of them down here. Wait a minute. Let me see something. I have one thing that looks a little screwy in the notes. Okay, let's not worry about that. Yeah, that's okay. Okay, now we're going to get, if we short asset 1, shorting asset 1 is a bad idea because we get lower expected rates of return, but we get higher risk. Okay, now when we go, if we short asset 2, now when we short asset 2, we get a higher expected rate of return than either of the two assets, but unfortunately we also get the cost of doing that gives us a higher risk. Here's the numbers I get, 9.82, and for this I get 10.82. Okay. Now let's do a couple computations here. Let's look at 0.6, minus 0.6. Okay, and then let's look at this RP equals 4.4 and see how that came about. So we have RP, R bar P equals W1 R bar 1 plus 1 minus W1 R bar 2, okay, equals minus 0.6 times R bar 1, which is 14, plus 1 minus a minus 0.6, so we have a plus 1.6 times 8 R bar 2. So this is equal to 8.4 plus 12.8. This is a minus, yeah, that's right, equals minus 8.4 plus 12.8. There's a minus sign here, equals 4.4. So that checks. That's the value we get there. Now let's see about the value we get for the portfolio risk here. Here we get 4.33. Okay, let's see. We can come down here. And we know what? We know that sigma p equals what? Equals the square root of minus 0.6 squared, that's a W1 squared, times 6 squared. Okay, that is sigma 1 squared plus 1.6 squared, and that's 1 minus W1, times 3 squared, which is sigma 2 squared, plus 2 times 1/2 times minus 0.6 times 1.6, and this is times, this thing here is times 3 times 6, and we take the square root of this whole guy. And this equals, let me move this up just a little bit here so we get it. This equals the square root, I get, of 12.96 plus 23.04 plus 17, this is a 4, 17.28, which equals the square root of 18.72 equals 4.33. So that checks also. Okay, so those two check here. Okay. Now, instead of going on and on with all these calculations, let's just say that the following. Let's take these, and all of these. Okay. And let's say good. Check these calculations. Results for extra credit. And we'll make this extra credit due a week from tomorrow, along with the others. So you should go through and check these here. That is much better than just watching me do some algebraic gymnastics here. Okay, now, so that corresponds to shorting. Now, let's point out something that we said. So, shorting and shorting, especially we'll talk about the asset with the lowest R bar can lead to higher and higher expected rates of return for the portfolio. And here's what we see that on our previous thing. If we short asset 2, the more we short it, the higher and higher the expected rates of return are. But also look at this. But also the higher and higher our portfolio risk as measured by the standard deviation is. Remember, this is kind of the converse of the risk premium. Remember, our idea of the risk premium is that if you bear more risk, you should get a higher reward. This is the converse. It says is if you're getting a higher reward on your portfolio, you must be doing this by bearing more risk. Okay. This should be sigma can lead to higher and higher RP, but at the cost, we'll say cost, of higher risk. Sigma P is measured by the standard deviation of portfolio. Okay, let's take an example. Let's take an example. Okay. Suppose we have our data. Let's just look ahead. Okay, suppose for our examples data, we do the following. We let W1 equal 11. Okay, so here we're really shorting, and W2 equal 1 minus W1 equal minus 10. Okay. We could think of this as the following. As for example, we started with $100 investing. with $100. So we could think of $100 as our initial budget invested in asset one, and then shorted $1,000 worth of asset two. Remember, we can do this. We can borrow stock from our broker, stock that we don't own, and then short it. And use this $1,000 to buy more of asset one. So we start with $100, then we short in asset one, then we short $1,000 worth of asset two, and use this $1,000 to buy more of asset one. So let's look at what we have. Then let's look at our portfolio rate of return. RP equals what? Equals 11 times R1. Okay. This is our W1 plus 1 minus 11 R bar 2. Okay. So this equals what? This equals 11 times 14 minus 10 times 8. Okay. This is a 14, of course, here. Equals 74%. Okay. So doing that gives us a really high expected rate of return, 74%. That's great. On an initial investment of $100. Here. Okay, that's pretty easy. Now, but we said that what? That our risk is going to go up also. Okay, so we don't get something for nothing. And let's look at this. Let's measure the risk by the portfolio standard deviation. That equals what? Equals the square root, W1 squared, sigma 1 squared, plus 1 minus W1 squared, sigma 2 squared, plus 2 W1, 1 minus W1, 1/2. Remember, this 1/2 is our row 1, 2, times sigma 1, sigma 2. See if we can, let's move this over a little bit. Times sigma 1, sigma 2, and we take the square root of this whole guy. Okay. Now, this equals what? This equals W1 squared is 11 squared times 6 squared. That's the risk on asset 1, plus a minus 10 squared, 3 squared, okay, and that's our sigma 2. This is 1 minus W1 squared. And then we have this 2 cancels with the half here. So we get the following. We get 11 plus 11 minus 10, 6 times 3. Okay. And we take the square root of this whole thing. So this equals the square root, by my calculations, of 4356, okay, plus 900 minus 1980. Well, this better be positive too. So it equals the square root of 3276, 3276. Which equals 57.2%. Okay. So we got this higher expected rate of return, that's 74%, which is really nice. But we also have a decent risk as measured by our standard deviation. So it's in the same way as that you should get a higher reward or expected rate of return for bearing more risk, that if you get higher and higher expected rates of return, it must be at the cost of bearing more risk. There's no free lunch here. Okay. So we can consider that the shorting case. Oh, okay. Now let's do the following. Here's an interesting thing here. Now, for our example, let's also calculate the value of W1 for which R bar P equals 0. This is where the line corresponding to shorting asset 1 crosses the horizontal axis. Okay. Remember that if we short asset 1, we got lower and lower expected rates of return, but we still got higher risk So it really never pays to short the asset with the lower rate of return. So let's just calculate this here. RP equals W1 R bar 1 plus 1 minus W1 R bar 2. And let's let that equal 0. So that's at the point where it crosses here. So this equals what? W1 times 14 plus 1 minus W1 times 8 equals 0. So what do we get? Now let's just gather terms here. We get 6 W1 plus 8 equals 0, or W1 equals minus 8/6 equals minus 4/3 equals 1.33. Okay. And remember, we only calculated the W1 up to minus 1 here. We have to go a little further. We were getting close. If we look at this, let's look at this. Yeah, we were getting close to, we were getting closer and closer to 0. But we weren't quite getting there. Okay. So you can also calculate that. Now, let's go and do something else today. Let's do that another day. Let's do the following. Okay. Now we're going to answer an interesting question. Let's answer the following. And also solve exercise number 4 of chapter 6. Okay. So essentially we're going to solve exercise number 4 of chapter 6 here. This is of the homework. So we'll do actually one of the homework assignments for you. Now from time to time I'll do that. Okay. So the question is, for what value of W1, and we'll call that W1 star, does our portfolio have the minimum risk, and that risk is measured by, in other words, minimum standard deviation. Okay. Okay. Now, how to do this? To answer this, we simply take the first derivative of sigma p squared. We'll use the variance. This is the same as minimizing the variance. We'll use the variance. The only reason we're going to use the variance is because it's easier to take the derivative of the variance than it is to take the derivative of a standard deviation. Remember, the standard deviation, we have a square root, so that'll be a little more messy than we have. So we take the first derivative of the portfolio variance with respect to W1, because we're trying to find the W1 that corresponds to that. Set this equal to 0. And solve for that optimal value of W1 here. We also have to note that we also must check the second order conditions for a min. And the second order conditions for the min are just we take the second derivative, d squared sigma p squared over dw1 squared, and that must be greater than or equal to 0. Remember, we had that graph like this. If you have that graph like this, you can see that if you want a minimum point, the minimum point occurs here at the bottom of that valley. And the second derivative, which measures the rate of change of the first derivative is a tangent. So the slope of the tangent is increasing and equals 0 there. Okay. And I think we asked for the second derivative to calculate the second derivative as an extra credit here problem. Actually, it's not such a big deal. We may do that too today. Here we go. So let's do this. Okay, we know what sigma p squared is. We know that sigma p squared, the portfolio variance, equals what? Equals W1 squared, sigma 1 squared, plus 1 minus W1 squared, sigma 2 squared. Okay, so those are variance terms. Then we have our covariance term, plus 2W1, 1 minus W1, rho 1, 2, sigma 1, sigma 2. Okay. Okay. Now, let's expand the second and third terms. Okay, so this equals what? This equals W1 squared, sigma 1 squared, plus what? Plus 1 minus 2W1 plus W1 squared, sigma 2 squared, okay, plus what? Plus 2W1 rho 1, 2, sigma 1, sigma 2, okay. And finally, we have plus, or actually we have minus 2W1 squared, rho 1, 2, sigma 1, sigma 2. Okay. Okay. So let's calculate this out here. So we have that W1, sigma 1, sigma 2. So now let's set this equal to 0 here. So now we're going to say d sigma p squared over dW1 equals 0 equals what? Now let's take this derivative here. This is our term, so what do we get? We get 2W1 sigma 1 squared minus 2 sigma squared, sigma 2 squared, plus 2 W1 sigma 2 squared that's right. Then we get plus W1 squared sigma 2 squared plus 2W1 rho 1, 2, sigma 1, sigma 2, and then finally we get minus 2W1 squared, sigma 1, 2, okay. No, we're on the wrong line here. Okay. We have plus 2W1 sigma 2 squared. Let's redo this. I'm back on the line. Okay, so we get 2W1 sigma 1 squared. Good. Minus 2 sigma 2 squared. That's right. Plus 2W1 sigma 2 squared plus 2 sigma 1, rho 1, 2, sigma 1, sigma 2, sigma 1, sigma 2, okay, good, minus 4, finally, W1, rho 1, 2, sigma 1, sigma 2. Okay. Now, let's see what we have. Let's factor out the W1 terms. Well, we gathered the W1 terms, you could say, and put them on the left-hand side. That gives us the following. It gives us W1 times what? Times 2 sigma 1 squared plus 2 sigma 2 squared minus 4 sigma 1 minus 4 rho 1, 2, sigma 1, sigma 2. Okay, and this equals the following. Equals 2 sigma 2 squared minus 2 sigma 1 rho 1, 2, sigma 1, sigma 2. 1, sigma 2. Okay, now now solve for W1 star. the one that minimizes this, we get the following. And this looks a little bit messy, but it's not so bad, actually. We get W1 squared, or just W1 equals what? In the numerator, we have 2 sigma 2 squared, minus 2 sigma 1 sigma 2 rho 1 2. So I'll just do that in a little different order. And on the denominator, we have the following. We have 2 sigma 1 squared plus 2 sigma 2 squared minus 4 sigma 1 sigma 2 rho 1 2. Okay. Now we could divide the top and the bottom by 2, but let's not worry about that. In other words, we could express this as the following. Maybe we will do it anyway. We'll get sigma 2 squared minus sigma 1 sigma 2 rho 1 2 all over sigma 1 squared plus sigma 2 squared minus 2 sigma 1 sigma 2 rho 1 2. Okay? So that's this is the value of the proportion of W1 to put in a portfolio if we want to minimize the risk on that portfolio. And this holds true for any value of the correlation coefficient here. Now, let's do the following. Let's do the extra credit too. To ensure that this value, this W1 star, yields a minimum variance portfolio we check the second order conditions. I think Leuenberger on the first part of this problem really wants to do it by Lagrange multiplier, but it's not necessary to do anything like that. We'll just check the second order conditions. That is d squared sigma p squared over dw1 squared must be greater than or equal to 0 for all W1, for all values here. Okay, so let's see this. Let's start this. I don't know if we're going to be able to finish it today. We may be able to finish it. Let's see this here. This is relatively easy, but there's a little algebra involved. Okay. Recall that the first derivative of sigma p squared with respect to a W1 was d sigma p squared dW1 equal what? Equals 2W1 sigma 1 squared minus 2 sigma 2 squared plus 2w1 sigma 2 squared plus 2 rho 1, 2, sigma 1, sigma 2 minus 4 w1 times rho 1, 2, sigma 1, sigma 2. Okay. So if we take the derivative of this, which will be a second derivative, would be d squared sigma p squared, dw1 squared. Let's take that second derivative. This equals what? Equals 2 sigma 1 squared. We got nothing for that. Plus 2 sigma 2 squared minus 4 rho 1, 2, sigma 1, sigma 2. And we want this to be greater than or equal to 0 for any rho 1, 2. Okay. We want that second derivative greater than or equal to 0. So now note that this is as small as possible when the third term is as large as possible. The first two terms are positive. The third term is negative. So if we want to check to make sure that that second derivative is always non-negative, let's try to make that third term as large as possible. This occurs when, obviously, when rho 1, 2 equals plus 1. Then that third term will be as large as possible. And if that right-hand side is positive, even when that third term is as large as possible, then we've checked the second order conditions. So let's just see this. I think we're going to finish here today. Okay. So what do we get? So when rho 1, 2 equals plus 1, what do we get? We get that this equals 2 times sigma 1 squared plus sigma 2 squared minus 2 sigma 1 sigma 2. Okay. Okay, so what does this equal? So if we complete the squares here, this equals either 2 times sigma 1 minus sigma 2 squared, or 2 times minus sigma 1 plus sigma 2 squared. And both must be are clearly positive. greater than or equal to 0 since squared. Remember, what we did here is we just completed the square. We said that this is like x squared, this is like y squared, and this is like minus 2xy. So we said that that's the same as minus x plus y squared I think we're finished now. Thank you. We'll go over that a little more the next time. Let's just go over here. Okay, good. Okay, let me give you this.